So, in the previous slides and recordings, we looked mainly at really net, the strong acids, and the calculation of their pH, and the strong bases and their calculation of pH. At this point, we're going to look at the weak acids and bases and their strength, their pKa and pKb. First of all, you remember that we said that a weak acid does not dissociate completely. And here's a weak acid, HA. And thus, this weak acid is governed by an equilibrium. And what dictates how much H plus gets into the solution is the Ka of this. And this Ka is called the acid ionization or dissociation constant. And of course, this has to occur in water. The bigger the Ka value, the more H plus I'm going to get into the solution, and thus this would be a stronger weak acid. What about weak bases? Weak bases also do not react completely with water. So the amount of OH minus that gets into the solution is governed by the equilibrium. Values, just products divided by reactants at equilibrium. Also, the bigger the Kb, the stronger this weak base will be. Now, in the next slide, we're going to look at that. pKa values and pKb values. Another point that I'd like to say is that sometimes in a base, you see that the base is not ionized. And the base is not an ion. So when it gets protonated, it becomes BH. Still governed by a Kb, now we have a new equilibrium constant. But this is no longer called the base hydrolysis. Now we can actually call it the base ionization constant, just like the acid ionization constant. Now, some people just call it Ka, Kb, dissociation, ionization, hydrolysis constants, that varies. Now, for a couple HA with A minus, both in water solution, the HA is governed by its Ka, the A minus is governed by Kb. Again, we're only doing right now when I add these two equations, okay, net, we can remove the HA here, the A minus, and you get a net equation which shows, voila, yes, you're right, it's the autoionization of water equation, which has a value of an equilibrium Kw. So we can say that Ka times Kb is Kw. And so at any time that I have a acid, I could always get the Kb for its conjugate or for the base of that acid. Either Ka, you can get Ka from Kb or Kb from Ka. And this is the same thing, same type of derivation that if I multiply Ka times B, substitute in equation, and for Kb, its equation, you will get H3O plus times OH minus, which is Kw. We also can take the minus log of both sides. If you get the minus log of Ka, minus log of Ka, plus the minus log of Kb equals the minus log of Kw, you get pKa plus pKw equals to 14. pKa, I can get at pKb. This is a very nice table because it just, tells me something about Ka and Kb for any couple. Let's look at some different acids, including our strongest acid, the hydronium ion. All of these strong acids will be considered in the form of the hydronium H3O plus because all of the HA, for example, or HCl, HBr, HI, all of them in the end, in solution, they become H3O plus in water. And here, so you have a list of weak acids. And let's look at the Ka values. That as the Ka increases, so the upward numbers, these numbers are increasing, the acidity, this becomes a stronger weak acid. My Ka increases, this becomes, the acids become stronger as the Ka is bigger. And thus, let's get the Ka for these particular Kas. Look, as my Ka is large, the pKa is small. The smaller Ka gets a higher pKa. And thus we can say that the lower the pKa values, the smaller pKa's right up here, are the stronger the acid. They are the stronger acids, not the strong acids. This, again, when they're weak acids, they're never strong. We already know the 6 strong acids, and you should know them. Now, as my Ka increases, look what happens to the Kb value. It decreases, of course, relative to this equation. So as my acid strength increases, the strength of the conjugate base of that acid decreases. The acid, the weaker its conjugate base. The weaker the acid, the stronger its conjugate base. But these conjugate bases are never stronger than OH minus. Right, we're going to actually, in the table above, we saw some negative pKb's and some pKa's which are greater than 14. And even here, this is a pKa scale. We see some negative pKa's for the strong acids. In this course, we're only going to concentrate on a scale which puts pKa 0 to pKa 14. And we're going to put this scale, let's say, vertically. We can go horizontally or vertically. On a vertical scale, we could actually relate the pKa to reactivity rule. I'm not sure that we really need this rule, but I'm going to discuss it anyway. Okay, so on a pKa scale, my most acidic would be 0, closest to 0. And the more basic would be at a maximum of 14. I will put the bases on the left-hand side and the acid on the right-hand side, each with its conjugate. So water will have a conjugate base of OH minus, HB will have a conjugate base B minus, and so on. Now, when do I use this? And when do I use this scale? And when do I actually put this line in? And why do I need it? I actually don't. There's a rule that says a stronger base always in a solution will react first with the strongest acid in a solution. So I don't really need this to tell me who's the strongest base and who's the strongest acid. If I know the Ka values and the pKa values, I will know. The lower the pKa, the stronger the acid. The higher the pKa, the stronger the base. Nonetheless, I mean, if you do put it, you can, simplify sometimes some things. So here, acid strength is increasing as my pKa decreases, and base strength is increasing. If I have in a system, for example, B minus and A minus, and I'm adding to them, and inside that solution, there's H3O plus. How do I know who will react first, the B minus with the H3O plus or the A minus with the H3O plus? Who will react first? And will B minus react with H3O plus and then A minus, or will they go at the same time? Now, I won't discuss the second part, but who will go first, at least? Well, who will go first is determined, of course, by the strength of this base and the strength of this base. Who's the stronger base? If I look here, the stronger base, B minus has a higher pKa, so it's the stronger base. So it will react with H3O plus first. Of course, that's exactly what this gamma rule is going to tell me. It's going to tell me that B minus will react first because it's above A minus. So B minus will go react with H3O plus, and that will be a acceptor of H plus, that will be the donor of H plus, and we go in the gamma direction. Now, does the opposite direction occur? Well, if we have nothing as a product, no, but if I have HB in solution and water, this reaction may occur, but that is not going to be a very spontaneous reaction. It's only spontaneous in the direction of gamma. Okay, so when we say gamma rule, we mean that it's the spontaneous type reaction, the fastest and the most spontaneous. So B minus reacting with H3O plus will occur before minus reacts with H3O plus, again, simply because the B minus is above the A minus or more basic than A minus. We already talked about weak is weak, so a weak acid will only create a weak conjugate base, and a weak base will only create a weak conjugate acid. Weak only creates weak. I will never, from weak, make a strong acid, for example. If I start with a weak base, I never get a strong base. Also, we already discussed as well that strong acids such as HCl, the conjugate of it, we shouldn't really call it conjugate again. It's better to be called a spectator or a spectator ion because there's no back reaction. Okay? And so all of the couple HCl, Cl minus, or H3O, NO3, NO3 minus, we don't write them as such. We only write H3O plus and water because all of these strong acids, all 6 of them, and go get the 6, will only create H3O plus in solution with a spectator ion.